And so, so the point of this paper is the theory. So let me recall the main story. So we have this group DFT1. So it is K between running and there is this group, so KRD. And maybe two, and there is a group KNR0, okay. You see the double shuffle, okay, and there is also the side of it. And okay, the main subject of today is to construct a group which is intermediate between this GX1 and T1. So this is the main result of today. The construction of it. Okay. So let me recall first how this inclusion was proved. So this inclusion here. So this was announced in the work of the Topology. And then later was proved by Finson. And later on, together with solution, so with using different kind of ideas in terms of technology and transformation. But then later on with solution, we gave a approach based on the ideas of the data. Okay. And so what I'm going to explain here is kind of so the development of this idea. Yeah. And if you carefully read what we are doing in the work with solution, you see that actually you have not only you can do this inclusion, but you can do that this inclusion factors through an intermediate. Okay, so this is the subject of today. Okay, so they're not proper, or not known to be proper. They are not known to be proper, so okay. I have a vague feeling that this is very good. So, these are some groups of work. In fact, all these are groups in one of the same big group, which we call star, and which are now recorded. So, what is G? So, I'm taking some kind of special notation, the notation of like the solution, but also the notation from the leader, it's not very standard. So I'm sorry. So this is in fact it was clean. I could let you K and topology is over the 0.1. And it has delta V, which is the product such that E0 and E1 are. Okay. Then you have invertible elements. and you have the group-like elements. And okay, and we will denote simply G. Okay, and then there are automorphism groups. So for G in group force, we define O G. So this automorphism group, it's an automorphism group. It's an element of the automorphism of K algebra of the R. Okay. Defined by E0 goes to E0. So E1 goes to E1, and E0 is belonging to some conjugation. Okay. And then you define the group flow here as follows. So we take elements in group force. This is out G, H, and products. And this is again a group. So this way you have it's called the Teichmüller group. And it contains G or V. And then there are the point is that you have two actions. Then you have G. So makes V part into V force algebra. So the algebra of the group. And likewise, we define V part makes V part. This is going to be the problem. And it's also a V force algebra. And the map is G not of G. Okay. And therefore, you have also an action.
So this is a transformation of the
No, it's a kind of product. It's a new product. It's a new product that is defined. So if you have a standard product in the form, you just take it's invertible elements in an algebra, so you take the product of elements, but you can also define two. Yeah, it's like big form has a square.
And then the commutator?
No, it's not the product. You take two elements, you have G and H. So you are taking the action of G on H, which is the new element in the force, and then you take the product of these two elements in invertible. So this is just an element in the force, and this also, and there is a right take the standard product of the two elements. And this is very important. Yeah. Yeah, this is the this is the the algebra. This is called the algebra, and then so yeah, it's all the G acting on A and then G. So it's a strange law, but you have a right to define it. And then the point is that this is a group law. This is called the Teichmüller group. So it's a the word for fascinate. And all this is the material for facility, all material. Okay. And then you are doing this, so you have an action on anybody part. And therefore, you have, if you are looking at the GMC of the part, so you are taking action by the different M3 of the. this divided into a group with action of over. And then you can define a semi-direct product and the same. And then you can define semi-direct products from this. And as well, over action of this, which we can pull back over G. Okay. And these are semi-direct products. You can define a semi-direct product. The semi-direct product with GFC of
Now ask a question. When you say GFP hat, it's the action bar out of G. So that what's the addition that I mean?
So you are if you are acting on if you are you have a group acting on that part,
yeah.
Then you also act on M of the circle.
Okay, the group is acting on that line. But the group acts on the vertical line as well.
It acts on L3 of this algebra, and you take an action on L3 of the algebra. And then you take the vertical to the algebra, so you are acting on it.
One question, like YGS3, right? I always again it kind of is mysterious, but I think I every time asking you and yes, but so what is it?
So the answer is pre-complete or something. Okay, so now everything is fine. So G is acting on A. Implies that P acts on MN of A, which is A times MN of P. So the action is here on time identity, and then we see algebra, and then there is a group action. And this is for so very good. So now so let's put category. So we are going to use PSGA for façon what itself is group action. There is a concept of this category so we are going to use it. So so this is a quadruple. So G. This is a group. This is a set. This is an element in the set, and this is an action. And this is a category. And there is a group from this category to the category of group, which is taking stabilizer. Okay. Good. And now we are the statement that we are going to define some objects. So lemmas. So we are going to take a form.
So it's actually necessarily how does this point X and X arbitrary, or is it satisfied?
Yeah, it's
any point.
Any point. The categories are codified. So, okay, there are like properties about this concept. So we are going to discover this properties so you are taking here this set of homomorphisms from V hat to M3 of discrete hat. So there is on this an action of the semi-direct product. So what is the action here? So if I have an element here, G acting on rho. Yeah, when split is the square of the curve. Okay. So this the action of G on rho is just so you are doing M3 of G V hat. Okay. Composed with rho with all G V1. Okay, this is the standard action. And if you have element P here, P acting on rho is at P composed with. So then you have an action. And you have here a particular element, okay, which is called the differential rotation. So given by formula. Well, the notation is that EI in V square. Okay. This is the definition EI times 1. And if you take Fi V hat, this is this peak, this is the square of the curve, and this is 1 times EI. Okay. So these are formulas that you can find in the international paper. So in fact, we have here about different solutions. There is no merit in this giving a one different algebra important skill. So taking any measure with the other this one is the solution. So, and the second statement is that so if you are taking star. So in fact, you can also take, so this is a left action by the way, and then split the left portion of GLP of V hat to this set. We take this set modulo this to GLP. Okay. So this has an action of just G itself, so we can and there is a particular element which is the clear string of the hat, not of the class of rho okay. Okay, and this corresponds to these are two objects in PLG. So, and this is also a reflex. And the point is that you have so you can take quotients and you get a multiple PLG tape. From one. And then it follows that you can take stabilizers and what you get. This is also the group in G, semi-direct G. Et here you have G, so you have solution here. Here a subgroup. And the point is that this is our okay. So in fact, it's a general property in the PhD lab that if you are taking quotients, then the more people at the level of simulation are so the consequence. Okay. So now, there is a double inclusion. So you have the diagram. And double inclusion. So, in fact, you have here T1. You have stabilizer. So here, this is so in fact, this is the same diagram here. So new new information is that this is the subgroup, in fact, of GL argument. Okay. And second information that the GRC1 is the subgroup of this. And third information that there is a link from this to this. So these are three statements. And now I want to prove this. So,
if I return to my previous question, you know, I mean, the answer that because in this diagram we have GS3, that's why 3 is important. Or if there's a more conceptual way.
Okay, so in fact, it's so you have to wait to listen all the time. The reason, so what we see by the what is the tree, the first one. Okay, so it's 3 years ago. In fact, now why we have to run a map instead of this particular model, this is question 1. So in fact, you can play the same game with any augmentation or any of them, and for many of them, there will not be such an injection. Okay, so the question is why for this particular augmentation, the injection of 0 to 1 will take place. Okay, and the reason is that, in fact, what I'm going to explain, so all the results is kind of so it comes from a particular construction based on modular spaces and which makes it related to the GRT1 or another rotation not okay. And light or high rotation we have here is reason they don't also the construction gives you something of maybe alternative construction to give you provide you more conditions which also would be a kind of multiplicator and which have the same property. So would be possible. What the interactor give you is this. Does not mean that the interactor cannot be extended. Okay. So maybe so the plan is one to explain GRT1 into this stub and this stub. And second is to explain that the stub is contained this demonstration. Okay. So let's go for the first. So now we need to use some kind of technology of moduli spaces and infinitesimal braid algebras. So in fact, there is pi 1 of M0n. So this is a group, and you are taking Grothendieck of it. So there is the Lie algebra of this group and the Grothendieck algebra. Okay, and this is which is called the infinitesimal braid algebra, and this is denoted Pn. Infinitesimal braid Lie algebra. Okay, so it's a graded. The algebra. So if you take P4, it's isomorphic to the 3D algebra in two generators, which is the 3D in two generators is 0, 0, which is the same as the primitive part of the hat. Okay. And the point is that by GT theory, so we take for any parentheses, so this is a set of parenthesizations of the word with 4 identical letters. Okay. And for any such parenthesization, you define a group action. Okay. And these actions are related by conjugation. So there is a map from a square of parenthesizations . So if you take out G, and the P satisfy co-cycle relation, which I don't. The first thing, you have these actions on this. The second thing, so is that you have morphisms relating the various Lie algebras and the.
So is this choice of parenthesization is just picking a tangential base point, and then you look at the corresponding action on. Okay.
The second thing is that you have for I in 1 pi, you have projection pro I from P5 to P4, which is a Grothendieck of what you get by forgetting one of the points in the mark point. Okay. And you have also a lifting map. Which is not a well-defined, which is kind of a doubling of points, which is not a well-defined, so which well-defines the level of pi ones, not well-defines the level of varieties. Okay. Okay. This second thing. So if you take care of profile, so U of profile, let us say, so you have so this thing, it's something of U of P5, okay, and it's isomorphic u p5 to the power 3. So here, let's say that in Pn, there are elements Eij, and this Eij correspond to point I or winding around point J. So Eij is a class of Ij minus 1. This is phi 1, so I around 4. So it's like I and J is here, like this. Okay. This is Xij. And so you have particular elements in U of P5, and the map here takes a triple and takes it to the sum of IA, I5. Okay. So from this, it followed that you have a representation. So you have algebra morphism. From UP5 to M3 of UP5, which takes A to so rho tilde of A and J, such that A E I5A is sum of rho tilde of A. Okay. So this is one thing. So let us call it as 4. Okay. So this is an algebra model. Okay. The second thing is that we come back at the level of group actions. So here, these group actions. So you have group actions on G on this algebra. These algebras are related by morphisms, and in fact, these morphisms are equivariant. Okay, so we are going to express this.
Sorry, can you say M3, even though there are 4 indices, because the sum of EI5 is 0 or something, right?
No, the sum is over 1, 2, 3.
What about 4?
There is no 4, so generators are this, it's a 3-dimensional. Because the sum of EI5 is equal to 0 over all I.
Yeah, because this 4, 5 is is linear dependent of. Okay.
Benjamin, if you think more geometrically, is it true that you have M05, M04, then the fiber is dimension 3, and you're taking the monotony of action of the base on the fiber, or let's say the p-Aleph, let's actually, because it's all linear.
Maybe it's this. Okay, we have to discuss it now. So now let's discuss a relation with group actions. So the point is there is also a collection of elements in V cross such that you have equivariance. For this map. So here you have action by, and here you have action by so the projections and these automorphisms, they intertwine up to conjugation by something. And from it, and also, same with L. Okay, so this implies, so you specialize for alpha equals 5. This implies that for any G in GRT1, you have the hot G P of I equals I. Okay, so from this you derive that for any G in GRT1, so you are taking particular elements in I, which are these generators, and you, in fact, you want to describe the action on the I. I is generated by the generator, so you just need the information of how does it act on this generator. So we are going to, so there is this unique CP of Gij, which is a matrix M3 in UP5, that you have hot G P of EI5 so always on G from 1 to 3, and this will be. Okay. And so the fact you can prove, so you can define in this way, is that you have a cocycle. So fact. Is a cocycle property, so it implies that so G maps to CP of G. So let's drop the indices. So it belongs to D1 of GRT1 with respect to GL3 of UP5. Okay. And so this is one thing.
Some kind of non-billion cost-out, you multiply. Some kind of non-billion.
And so you get, okay, up to now, this is it. Okay, and now there is a diagram. So in fact, there is a relation between this strange rho tilde and rho. Okay, and this is why rho de l'interosoma is so particular. So it's because it comes from this rho tilde. So in fact, there is a commutative diagram. So it's just a composite. So you have this L. And here you have so one. So you have M3 of 1 composed with the vector of. Okay, so there is, in fact, this. So in fact, rho has been contracting in this way. So rho comes from rho tilde through this construction. So this is it. So in fact, from it, you can derive. All this implies. So we have not too much time. So that there exists a commutative diagram. Like this. So you have this fact. So for energy. So add of something complicated. So you do HP1 times HP2 composed with like 412 of CP of D times P of K. So okay. What you can prove? This tells you that so. Here in this implication, so in fact, you need a complicated diagram, which I don't write on the blackboard, but which involves everything which has been written. Okay? And then the result is that this pair. So you call this C tilde P of G. The thing is that the pair G C tilde P of P inverse. This is an element in G semi-direct product with GL3 of the hat. So belongs to the stabilizer. Okay. Just say that rho is intertwined in this way. So this is one thing, and you can also prove by the same co-cycle property that the mapping G to this so is a group mapping.
Rho is rho dt.
Yeah. So okay. So in fact, we have 5 minutes left. So in fact, in these 5 minutes, so either I could explain this map in more detail, or I could give a short hint or why we have the next inclusion from the stabilizers in DMR0. So what would be better?
I'd like to hear about DMR0.
Yeah. Sorry, which map is injected? Or you said, where's the injection? You said, we were trying to prove an injection of something.
Any element in GRT1 satisfies this thing. Okay, so we said that in fact, so you have a lift, so you have with GL3. Okay. And GRT1 is a subthing in G. Okay. So this. Okay. Sorry. GRT1 is a subthing. So, and there is a canonical injection here. And there is this map is a lift to this. Okay. And here I have this stabilizer. Okay. And what I proved is that this indeed maps to this stabilizer. Okay. And since the image downstairs of the stabilizer is the other stabilizer, so it means that we in fact map to this stabilizer. Okay. The induction is just by construction because everything is a subthing in G. So you just need to prove it. Okay. Okay. So. So now, in order to relate, so second is relation with DMR0. So, in fact, let us construct the following set. A set of triples. So this is familiar thing. Okay. Then column. And row, this is 3, 1, and so the column vectors and reline vectors in V hat. Such that, so you have particular conditions. So row of V1 and so it's written in the note. So a column mod degree greater than 1 is a non-zero vector in case 3. And also rho is a non-zero vector. Okay. This is one thing. Okay. And then on this set, you have an action of a semi-direct product, which is a kind which is bigger than we had before. So on here we have the action of G. So again, G is acting, and you have GL3 acting, and also V cross. Okay. So this is acting. So there is a natural action. This is conjugation on row, and then standard actions on row and column vectors. And these are going to be opposite actions to the actions that you have by matrices. Okay. So the fact is that so you have there is a map going from set. So in fact, you have a forgetful map that you can forget one column. But what is more interesting, in order to do the relation with with the DMR0, is this map that I'm going to. There is a map from this from set to from W hat to V hat. So let me recall what is W hat. So W1 is an ingredient of the DMR0 theory. So W hat is K plus V hat E1. So it's a subalgebra in V hat. Okay. Okay, and there is such a map, and it is given by, so if I take a triple, it goes to the map 1 to 1 and AE1 maps to rho of A. Okay, and which is compatible with actions. And here at the left, you have the semi-direct action from so action from the semi-direct product. So it's compatible with this group morphism, the natural one. And the point is that, so if you take the image, a set maps to the set of homes, and you have above the set of homes, above the element of row de l'interasoma, you have column call row pair. So you have a particular element, the l'interasoma element. And such that the image of this element through this map, so this is going to be the particular element related again to double shuffle theory. This is I composed with delta W hat. So delta W hat is an element of double shuffle theory, and here you have generators yn, which is minus E0 to the n minus 1 E1, and there is a unique map delta W hat, which is an algebra morphism which is a coproduct on W hat, such that yn goes to yn times 1 plus 1 times yn plus the sum of yn times yn minus 2. Okay, so this is really in the paper of the Linter. Okay. Okay, and then the point is that so then there is a big diagram. I'm sorry for
the famous 15 minutes.
I'm going to be very short. So can we project maybe because I can explain on the, is it, it's written in the notes. So if you have the handout, so in the first page of the handout, you can see a big diagram. And here, the key point in the diagram is that you have strategy of the force. This is EMR0, and this equality is a long story. In fact, this long story is the first half of the node, so it's a long story. So there is a paper in particular that we had recently with Furucho. So it includes, but not only, the recent paper we had with Furucho this year, which is but there is also more ingredients, like we have Orchid homology, and so there is a lot of things. But in fact, finally, you have this equality, and then you have and so this is going to be equal to the step G of GL3 rho 0. So this is the step we are interested in. Okay, and the point is that here you have an equality. So so what are we doing here? So this is so in fact you have surjectivity from so you have an equality here. These are subgroups in G. Okay. and you want to prove equality between subgroups of this. So in fact, in order to do that, you show that these groups are surjective images of subgroups in G semi-direct product with GL3 of Bifrat. And this group I'm going to write, so it's a stab G semi-direct product GL3 of this element. And you have G stab in the same group of rho de l'interassommable. So you have here subgroups of the semi-direct product, and you want to prove the equality between these groups. So, and where does this equality come from? So, in fact, the point is that you have a map here, which is from, so I'm going to say the point is that you have this map from set to from, okay, algebra. And you have forgetful map. And the point is that it factors through big cross. So it's the bottom of page 3. Okay? So it factors through big cross. Okay. So this is clear. But the point is that in fact this map is injective. So it means that under this condition, so if two rows and columns give the same result, then they have to be related by the action of big cross. So the point is that this is injective, so you have an injection of sets with actions of this group. Yeah, and then it means that stabilizer should be the same. Okay, so the fact that this map is injective implies equality of the stabilizer. So in fact, it comes from this. So in fact, then you get the equality here of stabilizers. Then by surjectivity, you get equality here. And then after all, this map is not just a map, it's inequality, so you can include it and then go into the dimension. So that's basically the idea. Sorry for.
Are there any questions? We have time for maybe one or two quick questions.
It's not really a question, but at the very beginning, you mentioned the paper by Photoshop. Where it proves that GRs is included in the double solo, and they said it's inspired by the interassommable, but as far as I remember, it doesn't even mention it. It's not a matter of quibbling with references. Does it have anything to do with the interassommable, the paper?
No, I'm not sure he says it's inspired by.
Well, I don't care. I mean, does it have anything
but
to do
in any
with
case, so I do not know a relation between this paper and the.
Yeah, there is no relation.
That's a very good question. So one of the reasons people like EMR0 so much is because it's simpler, but it is compatible with the depth filtration, where GRT is not very amenable for studying the depth filtration. Does your intermediate stab enable one to study the depth?
So
the depth graded version of stab.
Okay, so the point is that you have a depth filtration at the level of the GRT, and then you can extend it, so you can give separation on whatever subgroup you have of. But then, if you are meaning about a broader Kramer business and this doesn't matter.
If there are no further questions, we thank Benjamin again.